Hey there, so in this little lesson here we're going to take a look at this worksheet that I passed out in class that had a bunch of different problems on it that are reviewing kind of all the math stuff that we've done in chapter 15. So there's a variety of different things that are on here. So each one of them's got basically 2 problems each, and I'm just going to go through and kind of show you the solutions. So in order to make this best for you, make sure that you get those couple of things and that you've worked out the problems yourself. Again, we're going to be dealing over with a couple of different things. We've got D was percent by mass, which is a concentration. We had E was molarity, and F is dilution. So these are the 3 big things that we are working on today in this particular lesson. So you might want to get your formulas out, get your notes out, whatever you got, but definitely get this worksheet out. It's going to do you the best if you've done it first and then watch this video after you're done to check your work. That's going to maximize your learning. Alright, so here we go, moving forward into the different examples of what we're doing today. Concentration, molarity, dilution. So this was problem number 1, was combining 27.5 grams of lead 2 chloride with 200 grams of water, and then what's the mass percent of the resulting solution. So I typically start these off by trying to figure out what my equation is. So my percent mass, or mass percent, is done this way. It's going to be the mass of the solute, there we go, divided by the mass of the solution. Key thing here is to make sure that you're using the solution, not the mass of the solvent. It's a really easy mistake to make. So when I set this thing up, I'm going to do 27.5 grams because that is my solute. That's the stuff that's dissolved in water. And in the bottom, the mass of the solution, this is a little bit trickier. The mass of the solution is actually the mass of everything. It's 27.5 plus, sorry, that should be a plus. Let me erase that a little bit here. So there we go, plus 200 grams. Again, why is that both of them? Well, it's because it's the mass of the solution. The solution contains the solute and the solvent. And then the last thing I'm going to do is multiply it by 100 to get to my percent. So if I do this all out, by the time I get my math done, it's, I don't know, before I do the 100, it's 0.120879 or something along those lines. Multiply it by 100, I get this kind of value, 12.8. And I'm going to stop at the 12.8 because of the fact that we've got 3 sig figs in our problem. So sorry, not 12.8, oh my god, 12.08. So it's going to be 12.1 if I could round, there we go. 12.1% is my final answer. Again, 3 sig figs because 27.5 has 3 sig figs, 200.0 has 4 sig figs. So you got to go with the least of the 2. So 12.1 is your answer. Okay, so here's problem number 2. We've got a solution that's 15% sodium hydroxide. There's 375 milliliters of solution. How many grams of sodium hydroxide would be present? So I'm going to kind of start back off here with my equation. Percent by mass is the mass of the solute, S-O-L-U-T-E, over the mass of the solution. And this one's kind of a little bit of a trick one. This is the big assumption that you have to make here, which is, I talked about it in class, but I know it doesn't say it on the worksheet itself. I edited that for the future. But the big idea here is that if you have 375 milliliters of solution, because water weighs 1 gram per milliliter, I can assume that that 375 milliliters actually weighs 375 grams. It's not exactly 375, but for the purposes of what we're doing here, you can make that assumption and we'll deal with it like that. So I'm going to plug these numbers into my equation. Now that 15%, that one up there, has to go on the left side of my equation. So there's my 15%. I don't know my mass of my solute. That's actually what I'm trying to find, the how many grams of sodium hydroxide. So that's my X. And then at the bottom is the mass of my solution. And again, I'm going to make that kind of leap of faith and call that 375 grams. Again, I know it's a little bit odd, but one of those little tricks that we can use. So, times 100 to make it in percent. So 0.15 is going to equal X over 375. All I did here, math-wise, was to divide both sides by the 100 to get this guy out of here and move it over to the other side. So that piece right there, just divided it over to here to move it into that. So by the time I do it, the next part is to multiply both sides. Again, algebra, multiply both sides by 375 to get my X by itself, and I get the value of X equals 56.25, and that's going to be a mass, so its unit is in grams. And then I check for my sig figs. If I look at my problem, I've got 3 sig figs in the 15% and 3 sig figs in the 375 milliliters. Therefore, my final answer here is 56.3 grams. I wouldn't have marked it wrong if you wrote it as 56.2 either, but 56.3 is more correct. 5 always rounds up if it's exactly 5. There you go. Answer 56.3. Moving on. What's the molarity of a 75 milliliter solution that contains 12.83 grams of potassium sulfate? So now this is a different kind of a question. Now we're dealing with molarity. We're not dealing with mass percent anymore, so that means I'm going to have to use my molarity equation. And molarity equals moles per liter. It's always what I'm going to end up working on. I always write it every single time. It just helps me remember what it is. So now if I look at the rest of my problem, what do I have? I've got this 75 milliliters. That's going to go on the bottom. That's going to go down here. The milliliters can end up in this spot. And then I've got this 12.83 grams. Well, it's going to go up in this spot eventually, but I can't put it directly there. You can't just plug in the 12.83. But I can put the grams up there. I just have to do a little grams to moles conversion first. So this is the tricky part with doing these, is to remember that you have to use molar mass. In order to use molar mass, I need to know what the stuff is, and it's potassium sulfate. Potassium, sulfate, potassium's a 1+, sulfate's a 2-. So there's my correct formula right there, is K2SO4. And I need that in order to be able to do molar mass. To figure out what the molar mass is, I kind of figured it out. 39.1 is for potassium. Sulfur is 32.07. Oxygen is 16.00 times 4. My total molar mass here for this particular substance is 174.27. Again, these are numbers from the periodic table. I'm adding them all together to figure out the molar mass. So my units of this grams per mole. Alright, so now we can get ready to kind of fill in our equation up above. I'm kind of working backwards from this. I need to find molarity. I can find liters pretty easy because I have milliliters. This is the one I'm working on, is trying to figure out the number of moles there. So the next thing I need to do is convert. I've got 12.83 grams of K2SO4. SO4, and I need to convert from grams to moles. So that's 1 mole K2SO4, and now I know it's 174.27. I never leave enough room, do I? K2SO4. So this is how I'm going to get the moles that I need to put on the top of my equation. By the time I answer this thing out, 0.736, something like that, moles is what my calculator says. So that's the number that I can put now in the top of my equation. That goes up here because I converted grams to moles, so I can plug the moles into my equation. The milliliters to liters is pretty easy. All I have to do is move the decimal place over 3 places. So now I can do this. 0.0736 moles of K2SO4 in 0.075 liters. Have to convert it to liters. Again, it's 75 mils. So I move the decimal place over 1, 2, 3 spots. So that's my final answer. Alright, by the time I divide all this thing out, 0.736 divided by 0.075, yikes, equals 0.9813. Again, you can grab the calculator if you want to. And then the final thing I need to do is check for sig figs. I'm going to write my answer down here at the bottom. With sig figs, looks like 75 mils has 2 sig figs, 12.83 has 4. So I have to go with the lesser of the values. My final answer would be 0.98. And then what are my units here? Molarity is my units. So I can write it this way, 0.98 molar, or I can write it this way, 0.98 moles per liter. Either one of those answers is considered correct. I don't care which one you use. You'll see me use that most of the time. So there you go, calculating molarity of the solution. Next. So here's the next type of way that we can use the molarity equation. This is one of those how do you prepare sort of questions. It's still just a molarity question. So we're going to start off with our basic formula that we have to deal with, which is molarity equals moles per liter. And then we can take a look at our problem and see what we've got. So how would you prepare 575 mils of a 0.8 molar magnesium acetate solution? So I can kind of start just by plugging and playing. I've got 0.8 molar, and I'm trying to figure out the number of moles. That's the part I don't know. And in the bottom, I've got 0.575 liters. And again, that's because you always have to have liters on the bottom, not milliliters. So after I do this part, how do I know that I'm solving for moles? Well, it's going to ask me how would I prepare. So how would I prepare problems usually mean I need to know kind of like how much solid to dump into the liquid. So I got to start with solving for moles first. Anyway, algebra wise, when I solve this out, I get 0.8 times 0.575 equals our moles, which if you do the math out on this, you get 0.46 moles of our stuff has got to be present here. So the last part is, I don't know how to add 0.46 moles of magnesium acetate to a solution, so I have to do a little bit more work here to finish this problem up. And again, if you take a look, there's a hint that I put in there which is solve for grams of solute. So if I've got moles, that means the last step I've got to do is convert from moles to grams. In order to do that, I need to know molar mass. I need to know, in order to do molar mass, I need to know the actual formula for this. So I'm doing magnesium acetate, because that's what it is in the problem. And so in order to do magnesium acetate, I have to figure out what the formula is. So there's magnesium, it's a 2+. Acetate is CH, 3COO. CH is a 1-. So that means I need to have 2 of them. So it's going to have a pretty big molar mass by the time we're done. If you get a periodic table near you, you can kind of see how this thing works out. Magnesium is 24.30. Carbon is 12.01 times 2 because of the 2 at the end there. This is 1.01 times 3 times 2 because we've got 3 carbons times 2 on the outside. We've got another carbon, 12.01 times 2, and then we've got 2 oxygens. I'm going to lump those together, 16.00 times 2, and again times 2. There's 2 of them here, and then we've got the 2 on the outside. So our total molar mass there by the time you are completely done is a relatively large number, 142.34 grams per mole by the time you add everything up. So our final step in this particular problem is to do our last conversion, which is to figure out how much 0.46 moles of magnesium acetate weighs. 0.46 moles, and then we'll do our molar mass step. 1 mole is 142.34 grams, because that's our molar mass. And our final answer here ends up being something like 65.473, nope, 6, something like that. And by the time I round it to sig figs, I get 65.5 grams. So when I'm saying how would I prepare, you're always going to solve for final amounts of grams. So what I would need to do to solve this, I would need to put 65.5 grams in enough water to make 575 milliliters of solution until it dissolved. And that's how you'd end up solving this particular problem. Alright, so taking a look at molarity of a resulting solution like this, kind of a hint here in terms of reading these particular problems. When you see that you're combining something, a solution that's already made, like lead nitrate, with water, that means it's a dilution problem. And this can be a little confusing at first for students because it doesn't say you're diluting something. But whenever you're adding water to it and you're changing the volume, that has to be a dilution problem. So again, I know it's not necessarily obvious when you're first looking at it, but you got to kind of start using your context clues to figure out how to, what am I doing here? Am I making a solution or am I just adding water to dilute a solution? So because it's a dilution problem, we're going to use our dilution equation. M1V1 equals M2V2. So the molarity and volume of our first equation equals the molarity and volume of our second solution. So what do we have here to start with? Well, I'm starting with 125 mils of a 0.25 molar lead nitrate solution. That's what I'm starting with up here. And the 650 is part of the after. It's part of volume number 2. So I'm going to start by putting these numbers in my equation to begin with. So I've got my first molarity is 2.5, and my first volume is 0.125. Again, that's in liters, not in milliliters. You'd probably get away with it, but it's one of those things you got to be careful with here. We're trying to figure out the molarity of the resulting solution, so we're trying to solve for M2. And then we've got this part about adding the 650 milliliters of water. And that means that we now have a total solution that's 125 plus 650. It's the total volume, and that's the big trick that students miss a lot of times when we're doing these. They want to just put the 650 in here. But remember, what you've actually done is you've added 650 mils of water to 125 mils of solution already. So it's a little bit of a different trick, but you got to kind of keep that in mind what you're doing here. So I'm going to start doing a little bit of algebra. 2.5 times 0.125, this over here is 0.3125. Over here, this is M2 times our new total volume, 775 liters is what we've got going on. So subtract, or divide it out, subtract, nice job. M2, if I do 0.3125 divided by 0.775, I find that my answer is, I don't know what that survey says, 0.4032 2, 2, and some change in my calculator. Looking back at my original problem for sig figs, I've got 3 sig figs, I've got 2 sig figs, and I've got 2 sig figs. So I need to write my answer in 2 sig figs, which is 0.40. This would be molar would be the correct answer for that, because that's the concentration of the new solution. Alright, here's another example of a dilution problem. Kind of a dilution problem the other way. It's sort of a how do you make, but it's a how do you make with dilution. So this is, you're starting off with some super concentrated solution, like hydrochloric acid when it comes in my big lab containers is 12 molar. That's obnoxiously concentrated. And I really want to make something that's much less, much more normal to use in my lab, which is 0.5 molar. So I'm trying to do a dilution here. I've got this super concentrated stuff. How much water do I need to add, basically, in order to make this much of my diluted solution? Again, it doesn't necessarily look like that, but if I have two pieces of information about the same solution, I'm talking about hydrochloric acid and I'm still talking about hydrochloric acid, this is a dilution problem. I'm just trying to figure out how to add water to it. So yeah, I've got another problem where I'm doing this one. M1V1 equals M2V2. And again, if you're not sure, you can kind of draw before and after. So here's my before. I've got 12 molar. And then what am I doing? I'm going to add some water to it of some sort. And I'm going to try to make a bunch more of this 0.5 molar. And it's going to have a lot more water to it. So again, it's another way to think about, how do I know if this is dilution or not? Definitely can be kind of a pain, I'm sorry. Alright, so solutions wise, now that I know that it's dilution, is actually the math part's not all that hard. My initial concentration, 12 molar. I don't know how much of that I need. That's the question's asking me about. How much of that do I need? It's like, how do you use this to prepare? So it's kind of like, well, alright, what do I need to do with it? On my other side, I've got M2. My final molarity is going to be 0.5. That's what I'm trying to make. And I'm trying to make 750 mils, 0.750 liters of this particular solution. So now it's just a matter of algebra to kind of figure out how this thing works. 12 times our volume equals, I think it's 0.375 by the time I'm done. V2, or V1, whatever you want to call it, is going to be 0.03125 liters. If I move this over 3 decimal places to 3, it's 3.1, yeah, no, 1, 2, 3, 31.25 mils is what that answer would be if I want to put it in milliliters. 2 sig figs, so it's actually 31. So the way I would use this to actually solve for this particular problem, how would I use this to prepare? So what this means is I need 31 milliliters of this ridiculously strong concentrated solution. So I'm only doing 31 mils right here, just a small amount. And I'm adding enough water to bring it up to 750 mils of water. And that kind of makes sense. I'm adding a bunch of water compared to the original concentrated stuff, and my final volume, or my final concentration is quite a bit less. So kind of makes sense, but again, the wording on these I know can be a little bit strange. So those how to prepare is probably going to be, if I'm just adding water to it, then we're talking about a dilution problem. Alright, last couple of problems, kind of getting you warmed up for doing some stoichiometry. So I know that these are kind of a old history, but for some of you things that are kind of scary. So this one, and when we're doing these sorts of problems, solution stoichiometry, they're almost always double displacement reactions. So here's an example of that first double displacement reaction. We'll do the math on the second slide coming up here. So your first part is to take this apart, this question, and try to figure out what the balanced equation is. So write and balance the equation and then identify the precipitate. So what do we got? Let's take a look at our problem here. What's the precipitate formed when you combine solutions of sodium carbonate, so there's chemical number 1, and nickel 3 chloride, there's chemical number 2. So I'm going to start by writing those out. Sodium carbonate is Na and then CO3. Sodium is a 1 plus, or 1 plus. Carbonate is a 2 minus. So therefore I need a 2 down here. I have to balance my charges. Again, don't forget, you're kind of writing that initial equation. You have to check that part to make sure you cross them down to get your final formulas correctly. And my second thing I've got is nickel 3 chloride. So there's my nickel, there's my chloride. Nickel 3 means it's nickel 3 plus. Chloride is a 1 minus. So I need a 3 down here. So there's my 2 initial reactants. Now I have to figure out what my products are. Again, remember, with products, it's kind of the inside-outside thing. They're going to switch partners and see what our new possible products are. So our first thing we're going to have is sodium and chloride. So sodium is that, and chloride is that. Now remember, these subscripts go away because the 2 and the 3 that are over here on this side, this 2 and this 3, are only there from balancing charges, so they don't carry forward. The only one that's going to carry forward is the CO3, because that's part of carbonate. That one's going to stay on the other side, but these ones aren't necessarily. Sodium is this, chlorine is this, sodium's a 1 plus, and chlorine's a 1 minus. So that is actually complete right there, 1 plus, 1 minus. Our other product is this inside one, nickel. Sorry, I got that wrong. Nickel right here and carbonate right here. This is going to be kind of a messy formula by the time I read it because the charges are different. So I've got nickel, nickel and carbonate, CO3. There we go. Nickel is a 3 plus. It does not change. Carbonate's a 2 minus. So that means we're going to have to do some parentheses and crossing down. So I'm going to cross the 2 down to the nickel and the 3 down to the carbonate. Yeah, it's kind of ugly. Ni2CO3, 3. There we go. So our two products are sodium chloride and nickel carbonate. Last thing we need to do is to remember to balance our equation, because we kind of have some messy stuff going on over here. So I'm going to start with my finding the most complex molecule. It's this thing. This nickel carbonate is by far the biggest thing, so let's see if I can get it to balance to that. So I've got 2 nickels and 3 carbonates. So now let's see how the rest of our equation works out. And so I've got 3 carbonates, 2 nickels, that works out. Now if I look over on this side, I've got 6 sodiums, and over on looking on this side, I've got 6 chlorines. So this equation will balance out nicely if I just put a 6 there. So, ugly. 3 Na2CO3 plus 2 NiCl3 yields 6 sodium chlorides, NaCls, and 1 of these monstrous nickel 3 carbonates, two CO3, 3. There we go. So sorry, that's a 2 right there. Yeah. I can try to erase it. There we go. So in terms of this, what's our precipitate going to be? Because that's the last part. Write and balance the equation and identify the precipitate. Well, if I look at my products here, I've got sodium chloride and I've got nickel carbonate. I know that sodium chloride is soluble, so that's going to be my aqueous one. That means my other one, nickel carbonate, is going to be my precipitate, so that's going to be the one that's there. And if I have a sheet of solubility rules in front of me, it's pretty obvious to tell which one of those works. So there you go, writing and balancing the equation, practicing with a little bit of double displacement. So now let's look forward and do the math on this beast of an equation. Okay, so here it is. I put the balanced equation here just so I don't have to write it again because my handwriting's terrible. So you're reacting together 0.2 moles of sodium carbonate, 0.25 moles of nickel 3 chloride. I'm going to label my equation. I've got this one, Na2CO3, sodium carbonate, 0.2 moles. And then I've got 0.25 moles of the nickel chloride, 0.25 moles of that. And the next part of the sentence says, how many moles of the precipitate would you expect to form? So we're trying to find this one. Don't care about this. The sodium chloride is there, but it's not what the question's asking me about. So remember, if I've got amounts of both of my reactants and I'm trying to find the amount of product, this is a limiting reactants problem. This is grilled cheese. I have to do both of them. So I'm going to do one problem from the sodium carbonate to the nickel carbonate, and I'm going to do a second problem from the nickel chloride to the nickel carbonate. I have to do both of those and then determine which is the smaller answer of the two. I made this one just in moles so you don't have as many problems to do. This is just kind of a review. So I'm going to start with the sodium carbonate one. I've got 0.2 moles of Na2CO3. And I'm going to go to nickel carbonate. Those are in a 3-to-1 ratio. Na2CO3 to nickel carbonate. 3 like that. They are in a 3-to-1 ratio. So by the time I math this out, it's 0.067 basically moles of that could be formed. And if I do the other reactant, because remember this is limiting reactants, I've considered the bread, now I have to consider the cheese. Now I've got 0.25 moles of this stuff, of the nickel chloride. There we go. NiCl3. And I'm going to convert nickel chloride, Cl3, do our mole to mole ratio to the nickel 2 carbonate, nickel 3 carbonate, NiCO3, 3, there we go. These are in a 2-to-1 ratio, 2 of those to 1 of those. And again, I'm using my ratios from here, and I'm putting them in these spots. Remember, I know a lot of you guys make this mistake. This 3 only appears in that problem. It doesn't get melded into this thing. Same thing, this 2 only appears in that step. It's the only time that you use that. So, math this out. How many moles of this am I going to get? 0.25 divided by 2 is 0.125 moles. Both of these are moles of nickel 3 carbonate. 3 Ni2CO3 3. So the last part, remember, with a limiting reactants problem is that you actually have to make a choice. Since we have two different answers here, there's answer number 1 and there's answer number 2, you have to make the selection. This one up here is the smaller one, so that's going to be our final theoretical yield. It's our theory yield, right? This one is incorrect, it's too much. So our theoretical yield is going to be 0.067 moles of nickel carbonate. That means that sodium carbonate was our limiting reactant. Remember, nickel carbonate cannot be a limiting reactant, it's a product, so be careful with that. And then that means that nickel chloride over here was our excess reactant, and we had too much of that around. So again, our final answer here would be 0.067 moles of nickel 2 carbonate, and then if I asked you to, it would be a pretty easy thing to turn that back into grams using molar mass. So there you go, there's a review of all of our different types of dilution and solution preparations and molarity, all kinds of stuff like that. It kind of pulls together a lot of the skills that we've seen earlier this year. So I hope this helped you figure out how to do these problems. See you next time.